Hello guys, good day everyone. Welcome to TGT Space, and in today's class we are going to be talking about BED calculations. We want to take a look at some calculations that we can have under biologically effective dose. So basically, what do you understand by biologically effective dose? So the biologically effective dose is used to express the radiation dose in their true biological effects. All right, so this is going to help us to be able to give the right comparison between different treatment regimes. So, and the question before us today, we can see that we've gotten three regimes: regime A, regime B, regime C. All right, and we've gotten different doses that are being used in each regime. So in regime A, we've gotten 60 gray of dose. Regime B, we've gotten 65. In regime C, we've gotten 55 gray. So this is the fraction. So the fraction is scheduled period through which the dose is being given, and we've gotten 25 for regime A, 30 for regime B, and same for regime C. So here we've gotten the days, the total days to complete the whole procedure, and here these are the tissues we are going to be talking about. All right, so the first one here is the squamous cell of the head and neck cancer. Squamous cell, head and neck cancer. And we also have the acute responding normal tissue. We also have the late responding normal tissue. So these are the things we want to take a look at. And as you can see, under the head and neck cancer, we've gotten the alpha to beta ratio being 10 gray. For the acute responding tissues, normal tissues there, we've gotten theirs to be 10 gray as well. And the late responding normal tissues giving us 3 gray. So the T delay, which is the kickoff time, we've gotten 28 under the head and neck. This is the cancerous tissues we are going to be focusing on. And at the same time, we are going to do some calculations under the acute and the late normal tissues at the same time. So the thing they ask us to find, according to the question, is it said assume the patient starts treatment on a Monday and is treated Monday to Friday each week. So the first question is for treatment regime A, this particular one. It said calculate the intended BED for this tumor. So we want to calculate the intended BED for this head and neck cancer. At the same time, we ask us to find for the acute as well as late responding normal tissue. So we are looking for 3 BED here. So but first thing we are going to talk about is what is the formula for the biologically effective dose. So here we are going to be talking about the formula as BED equals to ND into bracket 1 plus D over alpha beta ratio. Right, so this is the physical formula for BED. Right, so this is BED without time. So what is now, in this case here, we've gotten time, right? They've given us the time factors. So how do you now calculate BED with the time factors being given? So you can also use the formula of BED equals ND into bracket 1 plus this whole formula. You bring everything back here, alpha, beta, bracket close, minus, right? So we have the tumor repopulations into bracket of T minus T delay. So as you can see, we've gotten our parameters that are being given in the question again in the formula. So for us to now calculate the BED of the tumor, all the parameters that have been given, we've gotten our alpha to beta ratio, we've gotten the regime. In regime here, we've gotten the whole radiation dose that's going to be used, and we've gotten the numbers of fractions as times the day. That's the time, right? So first thing first, we don't have this value here. We are asked to find this value, right? BED. That's what we are asked to find, right? But as you can see, for the tumor, the BED of the tumor, that's what we want to look for first. As you can see, the alpha to beta ratio of the tumor is given as 10 gray, right? So we also have the T delay. So according to what we have here, this is the T delay, which is the 28 days. And the K is given, and that is what we said. The K, which is the tumor repopulation, the half is 0.9 gray per day after T delay. So this is the value we are going to be particularly using to calculate the BED of our tumor. So what's next? The first thing we are going to do is to find the dose per fraction. This is called dose per fraction, and it is given as small d equals to d over n. N simply means fraction. So in this case, what is the fraction that we are using in regime A? So this whole first aspect is for regime A treatment. So what is the fraction that is being used in regime A? The fraction is given as 25 fractions. And the dose, the whole dose that is being given is called 60 gray, right? So here we can calculate our dose per fraction to be d equals to 60 over 25, right? So in that case, we can have calculation. So we know where we are. All right. So that case, we're going to have 2.4 gray. So this is our dose per fraction. This is the value for the dose per fraction. It is going to be needed while we are using this formula to solve for the BED of the tumor. All right. So the next thing here is we want to calculate the BED of the tumor. In this case, we are using for regime A, right? So let me just put it here. Regime A. So we have BED, and we've gotten our N, right? The N is given as what? As 25 in regime A. So we can say BED equals. So let's break it down first. So I'm going to be taking out this particular formula. I'm going to be taking it out. So I'm going to be using the BED physical. Now the physical biologically effective dose formula. I'm going to use this one like first solve for this, then I'm going to substitute for this after calculating it separately. So I feel like that's going to like ease our understanding of the whole concept. So we are having BED to be equals to. So what's the fraction that's given? That's 25, right? So we have 25 multiplied by what is the dose we got here? This fraction, that is 2.4, right? So in the bracket of 1 plus 2.4 over, so what's the half to beta ratio that is given under the tumor is 10 gray. So we have 10 gray A. So in that case, we are going to be having 25 multiplied by 2.5, 2.4. It's going to be what?
So you don't know.
That's 60 now. That's 60.
Right.
Yeah.
So that's going to be 60, and we have 60.
We do not minus y. Minus to minus k.
Into brackets. So we are going to have 60 to bracket 1 plus this is going to be 0.24, right? So we can say that BED is equal 60 into bracket 1.24. So our final for the physical BED now of the tumor. So it's going to be BED equals. So this that is 70 point something like that. So that is 74.4 gray, right? So we have 74.4 gray, right? But this is not where we are stopping, right? This is the BED without time. Understood? So we also have the BED with time, which is where we got this formula.
Also, to do it for the man, it is BED without time. Then now before the BED with time.
So this is B with time, BED with time. So without time, this is for the time, right? So now we have to calculate our tumor repopulation, and it is actually given here, and that is 0.9 because this is the post date after the kickoff, which is the T delay. What is the T delay given? That is 28, right? But what is the exact day for the whole procedure? That is given as what? As 32. Alright, so the time for the whole process to accelerate is going to be T, which is 32, minus 28, which is the T delay. So in that case, we are going to be having, so let's just come to this end. We are going to be having 32 minus 28, and that will be 4. So that is, we have 4 days, and the K, which is our tumor repopulation, we have to multiply the K by the 4 in order to fix it into the formula back. But to make it more understandable, let me bring back the formula here. So we've already gotten this part to be what? To be 74.4 gray, right? This part, we've gotten it to be 74.4 gray. And this is the part we want to solve for now. and we've already calculated the t minus t delay. So, and our k is given as what? 0.9. So in this case, we can say BED equals 74.4 minus, so that is k, which is 0.9 multiplied by, right? Multiply by 4. Let me do it like that. So what's that going to be? So we have BED equals to 74.4 minus, this is going to be what? 3.6, right? Yeah, I think something like that. So if that's going to be the case, then we can subtract this and this. Then we are going to have 70.8 green. So our BED tumor is going to be 70.8 green. Alright, so this is the biologically effective dose for the tumor, alright, under the regime A. So what other thing they ask us to look for is for the acute responding tissue, the normal tissue there, and the late responding normal tissue. So it's just the same process we've gone through, but in this case, the acute responding tissue does not have any T delay, so there is no time loss here, alright? So there's no time loss like we did calculated here. There's no time loss, and same thing for the late. There's no time loss. So in this case, these acute responding tissues, it actually has the same alpha to beta ratio with the tumor. So if we use the same formula, which is the physical BED formula, to calculate for the acute, it's still going to give us the same thing as we've gotten for this. Alright, so it's just like we repeating the same process under the same regime, since they have the same alpha to beta ratio, like 10-10 grade. So the whole formula is going to result into this. Simply means that the acute BED is 74.4 grade at the same time. So but for the late BED, now the thing we want to do is, we don't have much space and I don't want to like be rubbing up the whole stuff. So the thing you want to do is, you want to substitute for your alpha to beta ratio in the equation. So in the physical BED formula, you want to substitute it for it in this area, then you calculate the whole thing. So the final answer is going to be whatever you get. Alright, so that's going to be the end of today's class. At the same time, you can do the same thing for regime B, regime C, to calculate for your, the BED of the tumor, BED of the acute responding tissue, and of the late responding tissue. So I hope you understand. If you understand this class, please do like and share. Thank you.